think for some of you there will be some things in this talk that you'll already have seen, but I promise you that there will be some new stuff that I don't think any of you have seen towards the end. So if you hang around, you'll be sure to see something at least new, if not interesting. So to start off with, for those of you who don't know me, let me introduce myself a little bit by showing some of the things that we work on in my lab. So we work on machine learning, reinforcement learning, and robotics. And kind of our approach to this kind of work is to take methods all the way from designing new algorithms and new models all the way to evaluation experiments on real physical hardware. So this is showing some of the robots we've worked with, from arms to hands to mobile robots like quadrotors. And this one here in the corner is actually a tensegrity robot that we worked on in collaboration with NASA Ames, which is a kind of experimental planetary rover. In today's talk, what I'm going to tell you a little bit about actually is deep reinforcement learning. So I'll tell you a little bit about why we should think about deep RL when it comes to learning sensory motor skills, robotic sensory motor skills, and so on. I'm going to tell you a little bit about what we can do with deep reinforcement learning. And then I'll tell you some of the bad news. I'll tell you about what are the big challenges, what are the things that are still very difficult for us to do. And then I'll tell you about two recent research topics where we've made some effort to try to address some of these challenges. I'll tell you about how we can address local optima in deep reinforcement learning by training highly stochastic policies. And I'll tell you about how we can address sample complexity by learning adaptable features for reinforcement learning. But to start with, let's talk a little bit about why we should think about deep RL if we're interested in learning sensory motor skills. So I really like this kind of example of a particular skill that humans do really well, and that's the task of catching a ball. So there's a quote that I sometimes show in my talks from an evolutionary biologist named Richard Dawkins, who wrote in his book that when a man throws a ball high in the air and catches it again, he behaves as if he had solved a set of differential equations in predicting the trajectory of the ball. And at some subconscious level, something functionally equivalent to the mathematical calculation is going on. So this is a view of the world that roboticists, for example, might find very, very familiar. It's saying that, well, we have perception, we have modeling, we have some sort of a system of differential equations that describes the world. We can take that system of differential equations, we can plan through it, figure out a motion plan, run to the location where we expect the ball to land, and grab it. But it turns out that what people actually do looks very different from this. It turns out, and this is some experiments that were done in the 1990s on baseball players, it turns out that when we actually want to catch a ball, all we do is we look at the ball, we fix where it is in our field of view, it's a dark dot against a light background, and then we begin running. And we use a very simple heuristic to modulate our speed. If we see that the ball dips down a little bit, we speed up. And if it rises a little bit, we slow down. And you can show with a very straightforward similar triangles argument that if you follow this simple heuristic, it's called the gaze heuristic, you'll actually arrive at exactly the spot where the ball lands and you'll catch it. Without having to understand anything about wind resistance, gravity, all you have to do is just control your speed based on the position of a dark dot against a light background. So this kind of sensory motor heuristic suggests that if we closely couple perception and control, and we can acquire the right rule that relates perception to control, we can actually get some robust and reliable motion skills to perform seemingly very difficult tasks without having to do all the really complicated modeling in the middle. And in fact, it turns out that for a variety of other sensory motor skills like locomotion, people have already manually gone through this process. For example, this is a video of a running robot from Boston Dynamics. This is another video of an animation system. This is some work by Staley and Koros. And in both of these cases, there's an underlying system of equations that governs the particular motion skill this robot is executing. That system of equations was largely constructed by a human engineer with a lot of insight into how locomotion ought to work. And it constitutes sort of a parsimonious explanation for this motion skill. So simple feedback rules exist for complex motion skills, and sometimes we can even discover them manually. So it seems like it would be awfully nice if we could optimize such controllers automatically for any skill that we want without having to get really talented engineers, biomechanics experts, and so on to try to design them for us. So can we optimize such controllers automatically? So in this talk, I'm going to tell you about some results with deep reinforcement learning that try to do this. I'm not going to go into too much detail about the technical equations in deep reinforcement learning, except insofar as necessary to explain some of the research. But let me introduce some of the basic ideas at a very high level. So very broadly speaking, deep reinforcement learning methods can be divided into two categories: model-free reinforcement learning and model-based reinforcement learning. Model-free methods operate on a very simple principle. You start off with some initialization for your skill, this sensory motor heuristic that couples your perception to your controls. Perhaps you have a large neural network or something of that nature that's initialized with random weights. You run it, either in the real world or in your simulator, and you get some trajectories. And sometimes these trajectories are good and sometimes they're bad. And then you simply take the good trajectories and you try to make the probability of the actions encountered along those trajectories to be more probable under your policy. And you take the bad trajectories and you make the actions along those trajectories less probable. And this will improve your policy. So you repeat this iteratively until you get a better and better policy. So this is model-free reinforcement learning. It basically corresponds to a kind of trial and error learning procedure. You can also do model-based reinforcement learning. In model-based reinforcement learning, we take a slightly different approach. Just as before, we're going to run our policy in the real world, but then instead of trying to do trial and error, what we're going to do is we're going to locally estimate, or locally or globally, we're going to estimate the dynamics of the underlying physical system. So we're going to try to actually construct some estimate of the equations of motion, and that can allow us to compute a gradient for how we can modify the parameters of our policy to actually make it better at the task. And there are many different kind of permutations on this that use either global models, local models, simple models, complex models, etc. But they all have this general flavor. You run something in the real world, update your dynamics estimate, use that dynamics estimate to improve your policy, and then repeat. And the thing that's going to allow us to use either one of these two techniques to acquire complex sensory motor heuristics, like the gaze heuristic or the locomotion skills that I showed before, is to use sufficiently powerful representation so that we can represent whatever sensory motor relationship the task calls for without having to know what it is in advance. A very good class of representations for this is deep neural networks, but the important thing is not for it to be a neural network or even for it to be deep, it's for it to be expressive and powerful enough to capture relationships between input and output that we might not know in advance. Okay, so let's talk about what we can do with deep reinforcement learning. And this part of the talk is going to be divided into three parts. First, I'm going to talk about how we can learn perception and control jointly, and I'll try to answer the question, is this actually better than separating perception and control into two separate pieces? I'm going to talk about how we can scale up deep reinforcement learning and actually examine whether we can get meaningful generalization out of it. One of the really interesting things about deep learning and computer vision, speech recognition, and so on is that we've seen really impressive generalization. So it'd be really nice to know whether this is something we can achieve with deep reinforcement learning as well. And then I'm going to talk about whether we can learn complex motor skills like locomotion using deep reinforcement learning. So let's start with perception and control. So to try to address this question, I'm going to tell you about some experiments that we did. These were actually done primarily by my student Chelsea Finn, where we tried to use deep reinforcement learning to learn a policy that combines vision and control. So here we have this robot. It's a PR2 robot. Information from its camera is going to be fed as input into a deep convolutional neural network, and the output of that network is going to be the sort of lowest level motor commands for the robot, which in this case are joint torques, feed-forward joint torques. The robot here is going to be attempting a fairly simple task. So it has a sensory motor loop, and it's going to be using that sensory motor loop to insert this little red shape into a shape-sorting cube. It's a very straightforward task. We can all kind of understand what this entails. But it does have the basic ingredients of requiring both perception and control. So the robot needs to figure out where this little box is, figure out where the hole is, and be able to construct the motor commands that will actually move its joints so that the shape goes into the right hole. And what we're going to do in this experiment is we're going to compare two different setups. One where we use deep reinforcement learning to learn a neural network that combines both vision and control. So the whole network is trained to maximize success in the task. And we're going to compare this to a more traditional robotics approach where we separate vision and control into two parts. One part, the vision part, is going to be trained with standard computer vision techniques using supervised learning. So we'll actually collect a data set of different positions of this little shape. We'll use an automatic method to label where the hole is. We'll train the neural network, the same exact neural network architecture to predict where the position of the hole is. And then we'll have a separate, small, fully connected network that will just take those predictions and attempt to perform the task. So the reason that this network has the same shape is just because we're trying to control for the architecture. So we're saying, given the same architecture, let's just train them in two different ways. Over here, it's trained end-to-end on the performance of the task. And down here, the vision part is trained with a standard computer vision method, and the control part only is trained with reinforcement learning. So this will allow us to study whether combining perception and control actually has any benefit for this task.
Sorry, just to be clear here, right? Both of them are neural net techniques. It's just whether or not you combine the training.
Exactly. So the question is not whether neural nets are good or bad. This is not going to answer that. It's just going to answer the question of whether doing control and perception together has any benefit over doing it separately for these kinds of tasks. Well, for this particular task, in fact. So it turns out that the end-to-end approach succeeds about 96.3% of the time, which kind of makes sense. It's not a very difficult task. You just have to put the red shape into the trapezoidal hole. But to our surprise, this kind of separated approach, where vision and control are done separately, actually succeeds 0% of the time. And this was actually quite surprising to us at first. We thought maybe something about the robot is not.
Sergey, you control the end effector.
The joint torques.
The joint.
The torques at all the joints. So seven torques.
7 torques.
Yes. So we kind of wondered what was going on here. So the first thing, of course, that we did is we checked whether our pose predictions from the vision system were accurate. Turns out they're accurate to about 1.5 centimeters, which is actually not bad. For a monocular vision system at this distance, 1 to 2 centimeters is about what you'd expect from a good method.
So for 7 torques, you compute the forward kinematics? Or
No, so actually the kinematics are not used here for the torques. They are. We do give it the end effector position as the proprioception input, so it basically has joint encoders. But the torques are just like literally the torque commands sent to the joints. They're actually effort commands because they're feed forward. But yeah.
So you compute the inverse dynamics?
No, just there's no inverse dynamics computation. So they're joint torques, not end effector torques.
Okay, so you take all the joint forces and you combine them? Or
No, so they're literally the commands to the motors at the joints. So I should say this is not what roboticists typically call force control.
Okay.
So there's no closed loop force feedback or anything like that.
Okay.
Yeah. All right, so the vision system is roughly where we expect it to be for monocular images at this range. The trouble is that this particular task, you can see here, we intentionally put a ruler over here, the tolerance for this little hole is just a few millimeters. So having an accuracy of 1.5 centimeters is just not good enough to do this task. Now, that might make you ask the question, well, why is this thing up here working? Because if the vision system can only get 1.5 centimeters, how can you possibly perform the behavior? And I think there's a very simple explanation for this, which is that you don't need to localize the hole to put the shape into it. You certainly don't need to know the vertical position because the robot is just going to push down as far as it'll go. You don't even need to get the perfect accuracy along both horizontal axes. If you perform a robust strategy where you slide the block along the face of the shape-sorting cube, you only really need accuracy in the perpendicular direction. So if you understand that you're going to be, in the end, performing a particular task rather than simply localizing the hole, the perception system can make the right kinds of trade-offs to maximize the performance of the entire system rather than optimizing some intermediate computer vision objective, which is really just something that we would have made up. Yes?
So the failure of second post-prediction, doesn't that more speak to the importance of feedback control as opposed to an open loop strategy?
Yes, I think that's a good way to look at it. It's just, in order for the vision system to understand how to provide the right signal for a feedback controller, it needs to have some sort of error signal that tells it what kind of predictions are good or bad.
And you don't have that.
Right. The standard computer vision approach would be to set, pose accuracy as your objective. I mean, you have to set some objective if you're using supervised learning.
But still separated. The vision system could give you a very coarse thing, and then a traditional position.
Oh, I see. So this is doing feedback control. So this part, the controller that actually takes in the prediction from the vision system, is still a feedback controller. So this is doing feedback. It's just doing feedback on the predicted pose of the hole, whereas this is doing feedback up here on the entire image.
So both have feedback systems.
Yes. Although one might argue that this one is doing feedback on a much richer signal. So the feedback control view, I think, still holds. It is a benefit. You can view it as a benefit of feedback control. It's just that here it's constrained by what the vision system spits out, and here it has everything. All right. Second question. Can we scale up deep reinforcement learning and actually demonstrate some degree of generalization? I hope I can get through everything. Okay, so to study this question, what we did is we set up kind of a more large-scale experiment, because to study generalization, you need to acquire enough data. So this is an experiment that I did with some colleagues at Google, where we actually set up a number of robots that are all going to collaborate together to collect a large data set to learn a single sensory motor skill. And the sensory motor skill these robots are learning is a skill of grasping, which shows grasping because it's a very useful motor skill, but also because it's very easy for the robots to compute their own reward function, because they can just check whether they picked up an object or not. So even though there's many robots, they're actually all learning one policy. So they're all combining their experience, and because they all have different objects, and we actually cycle the objects every day, they get a wide range of experience to learn from. And once they've learned, once they've collected this data and we can train a policy on it, we can actually see to what degree does it generalize. So the setup here is that there's a 7-degree freedom arm with a 2-finger gripper. It's going to pick up objects from a bin located in front of the robot, and it's going to try to do this using monocular images from an over-the-shoulder camera. The camera is actually a depth camera, but the depth channels were only used for baseline, so the method itself only used RGB images. So it's a monocular camera. It's not even calibrated, so different robots have cameras pointing in slightly different directions. The policy is going to update the motor commands at 2 to 5 hertz. It's going to continuously control the arm, which allows it to servo the gripper to the target. So even though the cameras are all oriented a little bit differently, because the robot can continuously control the arm, it can actually watch its own gripper, watch objects in the scene, and do continuous servoing. And this also allows the robot to fix mistakes. And the robot has actually no prior knowledge about grasping except for that reward function. So you need some way for it to know whether it's succeeding, and that's just engineered by hand to just check whether the finger's closed. But other than that, there's nothing in the system that's sort of grasp specific. It's a much larger neural network. This is a 16-layer convolutional network because we're going to have a lot more data. We're going to train this on about 800,000 grasp attempts. But the interesting thing about the system is that we can actually watch what it does. We can see how it generalizes to new objects, and we can actually observe the kind of emergent behaviors that we get when we train a grasping system like this from scratch instead of designing it by hand. So I'm going to show you a video that shows some of these effects. So initially, we're going to see a bunch of objects that are all roughly rectangular and blue. And for these rigid objects, the robot does very much what you expect. It kind of puts the fingers on either side of the object and then picks it up. It takes sometimes a little while to kind of put the fingers in a spot where it's happy with. So it's constantly predicting whether the grasp will succeed, and it only closes the fingers once it's confident in a successful grasp. For this next object, you're going to see something a little different. So this is a soft sponge. And here what the robot does is it actually pinches it in the middle. And this isn't an accident. So the robot actually performs this behavior consistently for deformable objects. In fact, early on in the data collection process, one of the first things it learned, even before it learned how to reason about geometry, was material properties, because the material properties will very strongly affect the kind of grasp that you should use, and soft objects can be picked up with these pinching kind of motion, whereas rigid objects require a little bit more sophistication. This is a very small object, the kind of thing that will be really difficult for a depth camera to see. This is an object that's heavy and also very awkwardly shaped, so the robot takes a little time to kind of find a good grasp point that's closer to the middle so that it's balanced in the gripper. And this is an object that's transparent, so this is, again, the kind of thing that for a depth camera would be really difficult.
So for the, you go back to the network, do you mind?
Sure.
Where's the
So this is actually...
where's the border?
Yeah, so this is actually, in the parlance of reinforcement learning, this is a critic rather than an actor. So it actually takes in an image and a motor command and predicts the probability of success. And then we actually invert this network at test time by using an optimization algorithm to optimize over the motor command. You could also train a separate actor network, but we just didn't do that.
Isn't the no prior knowledge a little misleading? You are basically training the thing, so that's where your prior comes from.
Correct. So what I probably should have said is no prior like hand engineered grasping system. So there's knowledge in the sense that obviously it acquires knowledge, and that's what it uses. Correct. Yeah. Thank you.
How many test cases you had to go through? How many trials?
So for these videos that I'm showing, it was trained on 800,000 grasps. We have some new results that will come out shortly where we basically try to see how far we can push it. The latest we have uses about 6 million grasps, and that will be out soon. We can also use multiple robots to learn more complex motion skills. So this is actually using a parallelized version of the same algorithm that we used for the shape sorting cube previously, but now it's parallelized across multiple robots that are all collaborating together to open doors. And again, we can study generalization to different door positions, different door angles, and also different door handles once we have enough doors to train on. All right, this third one will be, yes?
So you didn't, I don't know, I may have missed this. For new objects that you grasp, how large was the new data set of objects that hadn't grasped before?
I don't remember how many there were. So the success rate for the system obviously depends a whole lot on which objects you tested on. So it's only really meaningful kind of comparatively. But yeah, it was in the 80% range. We have, in the paper, we have a relatively small evaluation with about something like about 1,000 grasps on a small set of objects. In the newer version, we redid the evaluation on, I believe, 200 objects or something. So it's much more large scale, and that'll be out shortly.
But that had not been seen before.
Correct. Yeah. All right. So last point I wanted to cover is, can we learn complex motor skills like locomotion? And this will lead a little bit into the next part of the talk, when I'll discuss some of the new research that we've done. So this is some work with John Schulman, who's now a research scientist at OpenAI. And he developed this algorithm called trust region policy optimization, which is one of these model-free algorithms. So if you remember the discussion at the beginning of the talk, the model-free algorithms essentially do learning by trial and error. That makes them a lot more able to handle complex kind of non-differentiable systems like this walking robot, but also makes them a lot less sample efficient. So they actually need a large number of trials to learn these skills. So this algorithm was actually able to learn a complex running skill like this. It doesn't look quite like a person, but looks reasonably naturalistic. But I think it's actually very impressive if you think about this being learned entirely from scratch. So the only thing that is provided is a simulator, a reward function that says to run forward as fast as possible, and a neural network policy. Now, the iteration number at the top actually shows the iterations of the algorithm. Each iteration itself actually involves collecting several thousand trials on the simulated system. So while this algorithm produces very nice gaits and sometimes exploits bugs in the simulator to make the spider run forward really, really fast, it is not particularly sample efficient. It would be exceptionally difficult to deploy this on a real physical system. But it can really break your simulator. So that's going to lead into the next point of my talk, which is, well, what are the main challenges? And there are a few, and they're not always the most obvious ones. So first, the good news. We can combine perception and control with deep reinforcement learning. We can get effective generalization. And we can acquire complex skills with general purpose representations like the running skills I showed before. So now for the bad news. Oftentimes we have multiple solutions to the same problem, which is not unusual in non-convex optimization. But in RL, the problem is exacerbated somewhat because with these RL methods, they'll tend to heavily reinforce the first reasonably successful solution they encounter. In fact, the running skill that I showed you a few slides ago was one run of the algorithm. We can run the algorithm again, and we can get a successful gate according to the reward function that looks completely different. And part of the reason for this is that as soon as the humanoid discovers something that makes forward progress, it'll tend to reinforce essentially the first strategy it comes upon. So in the parlance of optimization, this is not at all surprising. It's a local optimal problem, but they're particularly prevalent for these kinds of optimization algorithms, these reinforcement learning algorithms. The other challenge is that high sample complexity becomes a problem, especially if we want to learn more complex skills that require these really data-hungry model-free methods. And what we're actually optimizing ends up with a very highly specialized solution to a particular problem. So even though the original representation for the policy is highly general, it's a large neural network, the final solution, the final policy that we get is highly specialized. It's trying to do one thing and do that one thing as well as possible. So in the subsequent two sections of the talk, I'll talk a little bit about how we can begin to address these challenges. So the first project I'll talk about deals with improving exploration by training highly stochastic policies. So here's a question we can think about. How can we explore very complex behavior spaces? So if we want to learn these running skills, maybe in order to prevent us from falling into these weird local optimi, what we should do is we should explore a variety of different strategies until we find one strategy that's clearly better than the rest, and then commit most of our probability mass to that, instead of prematurely trying to jump into the first effective strategy that we find. So what we can do is we can construct a much smaller, easier to understand problem that sort of encapsulates this challenge. So the small problem we're going to construct is this little spider maze problem. So we have this, it's not actually a spider, it has 4 legs. So if you're afraid of spiders, don't worry. But I'm going to call it a spider because it kind of looks like one. And the spider has to get to this blue square. As it gets closer to the blue square, it receives more and more reward. And once it actually steps on that blue block, it receives a really big reward. Now the trouble is that it can go either down or up. And if early on it decides to go up, it'll be really happy because it'll be getting more and more reward. And then it will commit all of its kind of resources to learn going up really, really well, and then it will get stuck against this wall. But if it arbitrarily chooses to go down in the beginning, it'll initially receive about the same reward, but in the end will be able to actually reach the blue square. So this is sort of a microcosm of the same kind of problem we're seeing up here, where in order to really succeed at this task, you have to explore both hypotheses until you find the one that's clearly better. So how can we track both of these hypotheses? So this is some work that was done by Thomas Harnoy and Haran Tang. And before I tell you about how this algorithm works, I need to introduce one mathematical formalism, which is the Q function. So the Q function is a very important concept in reinforcement learning. The Q function is a function of the state and the action of the system. It's a scalar value function, so for every state and action, it gives you a scalar value. And what the Q function tells you is the total reward that you'll get if you take an action A in state S and then act optimally. So this then act optimally part is important. So it basically tells you if you take this action and then after that you follow the optimal policy, what's the total reward that you'll get? Once you have the Q function, it's actually very easy to recover the optimal policy from that. You simply take the action that it has the highest Q value at that state. So the Q function essentially subsumes all the future consequences of your action. And in fact, one very popular reinforcement learning algorithm called Q-learning actually aims to learn the Q function with a stochastic gradient descent procedure. So this is the method that was used in the well-known DeepMind Atari playing paper. The high-level idea is to basically try some actions, see what their reward is, see what the total reward from those actions is, and regress onto those values. It's a little bit more elaborate than that, but that's basically the high-level idea. And then, of course, once you have the Q function, you take the best action. So this is sort of the standard Q-learning procedure. And now let's think about this little toy maze example. So if we try to imagine what the Q function for the spider will look like here at the beginning, it'll probably have two peaks. So, of course, I'm abstracting things away. The spider actually has more than one action dimension, but if you imagine that it was one-dimensional, it might be something like this. There's two peaks, one for going up, one for going down. One of the peaks might be randomly bigger than the other in the process of learning if you haven't completely figured out what the optimal solution is. Once you figure out that going down is best, then one of the peaks will be clearly bigger than the other. But until you figure that out, they might be roughly the same. One might be randomly bigger, so you might commit a little bit more probability mass there, and you'll just keep reinforcing that big peak. So if you try to take the best action with respect to the Q function, you'll arbitrarily choose one of the directions. You can do some exploration. You can add Gaussian noise, or you can randomly take random actions. But you'll still prefer the one that you randomly found to be more successful, just because that's the place where you learn to go first. So what we can do instead is, instead of preferentially choosing the best action according to the Q value, we can place our probability mass onto the different actions in proportion to the exponential of their Q value. There's actually a kind of a deeper mathematical reason why we use an exponential function here, but for the purpose of this discussion, it's just some positive transformation of the Q function. So what this says is that the best action will get the most probability mass, but if there are two actions that are tied, they'll actually get the same probability. And if there's some action that has a lower Q value, it'll still get some probability mass, it'll just exponentially degrade as the Q value decreases. So if you follow this kind of policy, you'll actually explore both the upper and lower passage until you find that one of them is clearly better than the other, and then you'll commit more probability mass there. So if you can represent a policy like this and actually capture multiple modes, then you can begin to address this kind of problem. So the trouble is that, of course, representing this kind of policy is quite difficult. It can be an arbitrary, complex, multimodal probability distribution. So what we can use is we can approximate this distribution with a stochastic neural network. And this stochastic neural network is going to take in the state, it's going to output the action, but it's also going to take in a noise sample. You can use whatever noise distribution you want. A convenient one is to use a spherical Gaussian. Don't cringe, Ben. I know this is this is the kind of thing that you cringe at sometimes.
Is that the right way to go? I'm just trying to think. So Q is positive, right? Q's not usually not negative.
Q can be negative, actually. Yeah.
I know, that's why this stuff.
It often would be, in fact. Yeah. So the deeper reason why this is an exponential has to do with how maximum entropy models work. In fact, this thing is actually sometimes called a maximum entropy policy. But that we can talk about after the talk with a whiteboard. So we'd like to train this stochastic policy so that when it takes in spherical Gaussian noise, it'll output actions that actually look like samples from this exponential Q distribution. And it turns out that we can do this using a procedure called amortized Stein variational gradient descent, which sounds like a really fancy term, but it basically amounts to doing gradient descent with an additional term that pushes the different actions apart for different samples from the same state, which forces the network to use the noise sample. And you can actually show that using this algorithm, you can train this network to create unbiased samples from this distribution, at least approximately, insofar as it's able to represent them. This method was actually originally proposed by Wang and Liu for generating natural-looking images. So for a GAN-like method where they wanted to sample images with natural image statistics. And in this work, we actually, Thomas and Harun actually adapted it to representing this exponential Q distribution to enable exploration for problems like this. So we ran this method on some toy examples to see if they can actually capture complex multimodal policies. So in this example, it's just a little 2D environment where your little point robot gets to walk left, right, and up, down. It's a continuous action space, and the reward function has 4 peaks. So these 4 little hills. So the right policy, the right maximum entropy policy, is going to commit probability mass to these 4 peaks in proportion to their rewards, and their rewards are equal, so it should commit equal mass to all 4 peaks. And we find that with our method, in fact, that's what happens. And these little insets here show the action samples, so the black dots are the action samples, 4 different points in this graph. So this yellow dot right here, that's here between these 2 peaks. You can see it has high Q value over here, high Q value over here, and the samples are placed kind of in the direction of both of these peaks. So this method is, in fact, learning something that's multimodal. And we can see what it does on some more complex continuous control problems. So this is a little swimmer task. So there's a little 3-link swimming robot, and it has to swim in a particular direction. Now, the reward function for this 3-link swimmer gives it a positive reward regardless of which direction it goes in. So it just gets a positive reward the faster it swims. But, so it can swim forward or backward. But there's a green finish line, and if it crosses this green finish line, it gets a really big reward. So initially it doesn't know which way to swim. It can swim forward or backward. And the optimal strategy during learning is to explore both directions until it finds the green finish line and then commit all of its probability mass to the forward direction. And what I'm going to show you here in 3 columns, this right column is our method called soft Q learning. And these left 2 columns are 2 different runs of the same deterministic reinforcement learning algorithm. So this is actually 2 different runs. And this is meant to show that on different runs, this algorithm will actually make an arbitrary choice about which way to swim. So in the first iteration, obviously nobody knows what they're doing, and they're just flailing at random. After about 100 training epochs, as you'll see next, they're going to start swimming in some direction. So one of these random seeds randomly decides to go forward, the other one arbitrarily decides to go backward, whereas the soft Q learning takes a little longer to learn, but you can see that it's sometimes going forward and sometimes backward. So it's actually already figuring out that there's 2 modes to this problem, but it hasn't yet figured out which mode is best. After 200 epochs, the soft Q learning method consistently swims forward because it's now figured out that it can cross the finish line and get the big reward, whereas for the deterministic method, if it got lucky and learned to go forward, it'll go forward, but if it got unlucky and started with a backward strategy, it'll continue to reinforce that backward strategy. And we can also look at the little ant maze problem, the spider maze. And here I'm going to show you different runs for the deterministic method. And you can see that when we ran the algorithm once, it committed most of its probability mass to the upper passage. We ran the algorithm a second time, starting from scratch, and it arbitrarily chooses to go down. So sometimes it goes up, sometimes it goes down. And then as you'll see next with the soft Q learning method, it's actually going to explore both passages. So that's coming up next. So here with the soft Q learning method, sometimes it goes up and sometimes it goes down on the same run of the algorithm. So it's actually a random policy that's choosing either passage. Now, one thing we can do with these stochastic policies is that we can actually use them to create a really good initialization for then fine-tuning a policy with a more specific goal. So what we're going to do in this next experiment is we're going to actually train the spider to walk in any direction it wants. So again, on the left, I'm going to show you the deterministic method with some random noise that's being injected. So it's still random, but it's not actually devoting that probability mass in proportion to the Q values. And on the right is our method, the soft Q learning. And you can see that with the soft Q learning, I know it's kind of a terrifying video with all these millions of spiders, but with the soft Q learning, it gets kind of pretty even coverage with all these spiders running in different directions. Now that's a fairly kind of qualitative comparison, and maybe a good question to ask now. Well, is this good for anything? So what we're going to do next is we're going to initialize a policy from either this deterministic policy or from the random soft Q learning policy, or just from nothing. So this is initialized from nothing, this is initialized with deterministic stuff, and this is initialized with the soft Q learning policy that runs in all directions. And here, the robot is now given a more specific task, which is to run in a very particular direction down this narrow hallway. On the first epoch, again, none of them are doing anything particularly sensible. This one flips over, this one is running in a random direction. But once they practice on this environment a little bit, we'll begin to see that the method initialized from the random soft Q learning policy is going to be making somewhat more rapid progress. So after 100 epochs, this one gets a little bit further, and then after 200, there's sort of a clear winner, and the one that was initialized with soft Q learning is able to get much further down the hallway because it had this initialization that already kind of knows how to run in all different directions. And these are the learning curves for this fine-tuning experiment on different kinds of hallways. The blue line is the one that was initialized with soft Q learning. The green line was initialized with a deterministic policy, and the orange one was initialized at random from nothing.
Sergey, are you I am not.
I'm not surprised. I think it's good to validate these things, because just because you can get a random policy doesn't mean it's actually good for anything. For me, the thing about this that's interesting is this idea that you can perhaps train a system to perform a particular task in all possible ways. To me, I think that there's something really interesting about just saying, solve this problem, but not just in one way, try to find all the possible ways to solve it. I think that's something that can be actually really useful. It can be useful for this kind of fine-tuning experiments, and maybe it can be useful for some other things too. All right, so some potential benefits. We can get better exploration out of this. We can get better initialization for other skills. Perhaps make a little bit of progress towards overcoming some of these local optimal problems. In principle, we should also be able to get robustness from this. So if you can train maximum entropy policies that solve a problem not just in one way, but in many different ways, that should be a more robust solution for these locomotion skills. We haven't evaluated this in detail yet, but that's something that we're exploring next. And then there's also actually some evidence in biomechanics that the way that people perform motion skills actually has some of these elements of maximum entropy control, where people exhibit actually greater variance along trajectories in places that are less important to the goal. So if you perform a reaching motion, you'll be very precise at the end, but you'll actually exhibit quite a bit of randomness in the middle. And this was explored in a number of studies. This is just one of the studies that showed this. So perhaps there's also some connections here at how we might do motor control. All right, so the last topic I'm going to talk about is how we can address sample complexity by learning adaptable features for reinforcement learning. So here, let me back up a little bit and talk about what it means to have useful representations. One result in deep learning that I think was actually quite interesting is that if you take a very large data set of images and you train a deep convolutional network to classify those images, you might do a very good job of classification, but you actually get something more than that. If you actually pull out the features from this deep network that was trained for image classification, you'll find that those features are actually broadly useful for a wide range of other visual perception skills other than just the ones that the network was trained on. So something about solving this big problem for image classification actually gives the network some understanding of the visual world that's useful for other stuff. So one question I have is, well, where are the ImageNet features of motor control or sensory motor control? Why can't we solve some really big reinforcement learning problem like that running humanoid and get features that we can then use for lots of other stuff? So maybe for when it comes to reinforcement learning, the story is not quite so simple. So the trouble with RL is that if you look at something like ImageNet, it's a large-scale problem that emphasizes diversity and is evaluated on generalization. Reinforcement learning problems, typically, at least the ones in the literature, are smaller scale. They emphasize mastery rather than diversity, getting a really high score on some task, and they're evaluated on their final performance rather than generalization. So perhaps if we want these really powerful generalizable features, maybe we can try to make this look a little bit more like this. So one way we can get started on this is we can formulate a kind of a multitask reinforcement learning problem and see if we can actually force an RL algorithm to acquire generalizable features. So this is some work done by Chelsea Finn. So you have this neural network policy. It has some parameters theta. And let's say that we'd like to learn a policy for our spider to run forward. The standard model free thing to do, let it run forward a whole bunch, take our samples, increment our parameters by the gradient of the reward of those samples. So this is sort of abstracting away a very generic version of a policy gradient algorithm. You want some gradient of your reward, and you add that to your parameter vector, and that gets you your new parameter vector, which is hopefully better with respect to reward. So far, so good. So perhaps if we want to encourage diversity, we might say that, well, let's have all these spiders running in different directions. Each of the different directions is a different task. And then when we update our parameters, instead of just blindly improving the reward of all the tasks together, which are, in this case, mutually exclusive, of course, because it's running in different directions, what we'll do is we'll actually do something very peculiar. We'll say, let's compute the gradient of the update for any given task. So I here is going to index tasks. This is the update for a given task I, so this is with respect to the reward I, and we can actually compute the gradient of that update. So this is saying, if you change your parameters and then take one gradient step in the direction of that task, how much better will you get? And then this is the gradient that we'll actually use to increment our parameter vector. Now this is a little bit weird, so let me try to illustrate this with a picture. Maybe this picture will actually make everything worse, but hopefully it'll make it better. So the solid line here, the trunk, this is showing the trajectory through the space of parameters during learning. At every step, you compute a gradient in the direction of all the different tasks that you have. And then you take a step such that this gradient update becomes better by as much as possible. So you're essentially trying to find parameter vectors that, when you perform one update on them for a given task, they'll improve that task as much as possible. one way to look at this in the parlance of dynamical systems is you're trying to maximize the sensitivity of these reward functions for all these tasks to your parameters. If you do this, you're essentially optimizing for features that are for parameters that are easy to adapt to new tasks.
Where do you get the RIs? This is just how it
You have to get them somewhere, yeah. So in this case, we say, okay, we'll have the thing running in different directions. Getting the RIs automatically would be really nice.
So you're taking the gradient of the gradient update? Is that the idea here?
Yep.
Okay. All right.
Yes.
Well, that's a fun.
It's a little weird. But it turns out to actually do some really interesting things. So before I show you some of the reinforcement learning experiments, let me illustrate this method on a toy example. So the toy example here is regression onto a sinusoid. So you can create a family of tasks that are regression onto sinusoids with different amplitudes, different phases, and different frequencies. You can generate a bunch of random sinusoids, train your neural network to regress onto all of these sinusoids. That's, of course, impossible because they're mutually exclusive. But you'll learn some sort of average sinusoid, which is what's shown in this kind of light blue line here. And then you can take that network, you can give it a new sinusoid, sample some points from it, so the triangles show the training data. There's just 5 points. And you can fine-tune that network on those points. And it'll get a little bit better slowly. So the dotted line here there shows the result after 1 gradient step. The dashed line is the result after 10 gradient steps. So that we all understand. It learns slowly, but it eventually gets there. If instead you treat all those different sinusoids as different tasks and use this algorithm, which is called model-agnostic meta-learning, to learn this network that can quickly adapt to new sinusoids, then you can actually see that after just 1 gradient step, that's shown in the dotted green line, it already captures much of the structure of the sinusoid. This example on the left is particularly interesting. Here, all the 5 sample points are on this right side, so it actually has no points on this other peak. Despite not having those points, the dotted green line actually already captures that peak after just 1 gradient update. So in the process of meta-learning, it actually captures something about the structure of sinusoids, so that just with 1 gradient update, it already gets the idea of what the sinusoid should look like. All right, so that's a simple kind of regression example. But I motivated this by saying that we'd like to learn generalizable features for reinforcement learning problems, so let's see if we can do that. So here what we're going to do is we're going to take our favorite spider, and we're going to train it to run forward or backward. And then we'll try to get it to adapt very quickly to running in a particular direction.
Why doesn't he have 8 legs?
Well, sometimes each leg is kind of costly. It has 4 legs because that's how John Schulman made the task originally. So if you look at the policy that we get just after the meta-learning process, it's not particularly interesting. It's sort of learn to run in place. But because it was trained with this meta-learning procedure, if we give it just 1 iteration with, I think it's about 10 rollouts for a reward that tells it to run forward, it immediately figures out a very fast forward run. And if we start from the same policy and we give it just 1 iteration with rewards running backward, it immediately figures out a backward run.
What were the rewards you were giving it in the meta-learning?
So in this case, it's just forward and backward. So this is not generalization. This is just saying did the network capture both behaviors so that it can quickly adapt. The generalization experiment we did was with different velocities.
I got it. I'm just trying to make sure I understand. So the meta-learning you train with both forward and backward. Now you get into this weird metastable state, and as soon as you say forward, it goes.
Exactly. So this is just testing that it is in fact in that metastable state. Right.
I really think that the key point you made, and for your understanding, is that selection of the parameter that will give you a smooth surface.
Exactly. Yeah.
Okay. This is not true when you take configuration space.
Right, exactly. And it's actually very important that this is in the parameter space. And this is why I motivated this by talking about the ImageNet features, is that the thing that ImageNet features do is they transform your space into something that's a little bit better for adaptation. Yeah, thank you. And we can use this for some other tasks. So this is kind of a similar idea. We're going to be running forwards and backwards. This is a little kind of planar cheetah. Again, after meta-learning, it sort of runs in place. After we fine-tune it with a backward reward, it learns this really kind of nice backward gait. And when we fine-tune it with a forward reward, it learns to run forward, and it's very excited, so it does the forward cartwheel, and everything is happy. All right, thank you very much.
In
Yes?
the meta training example that you showed, did the features that you extracted out of the meta training? Were they interesting or like they're representing something about the
We don't know yet, but I think that'll be really interesting to study. And I think it'll be particularly interesting to study that for more complex tasks. Ones, something like the humanoid task with many degrees of freedom, to see if there are actually things like motor synergies that start to emerge. But unknown yet. Yes?
How does the Q function relate to cost to go? In that
It's a synonym. So cost to go comes from optimal control. Q function comes from reinforcement learning, because reinforcement learning people like to be rewarded, and optimal control people like to pay a cost.
Minimize the Q function with respect to the action. It's the cost to go. They're different.
Well, minimize the negative Q function.
All right, well, they're close. They're close.
All right.
That's a hard